So first of all, thanks for the opportunity to speak here. It's really great to be at NYU, see some old friends. So I'm going to discuss first broadly and then very specifically some aspects of quantum gravity in asymptotically flat spacetimes, mainly with the idea of making analogies with the ADS CFT correspondence, but with different asymptotics. So this is roughly what I plan to discuss, but I don't need to get through all of it, so please interrupt with lots of questions. I'm going to start with some very sort of broad and vague points about the holographic principle in asymptotically flat space as opposed to anti-de Sitter space. And then sort of within a particular approach to quantum gravity and holography in flat space, I'm going to discuss a couple of very tight structural similarities between the ADS CFT correspondence and this sort of bottom-up approach to holography in asymptotically flat space. So I'm going to discuss sort of common statements in ADS, like when you have a gluon in the spectrum with gravitational theory, you get boundary conserved currents. When you have a graviton in the bulk description, you get boundary stress tensors. That's a little bit of an older result, and then I'll discuss something newer, which is the statement that when you have continuous spaces of vacua in asymptotically flat spacetimes, that maps onto the conformal manifold of this Euclidean conformal field theory dual. That's exactly the same statement that applies in anti-de Sitter space. And then finally, if there's time, I'm going to use this description in terms of continuous spaces of vacua to rephrase in an interesting way some old statements about the BMS group and groups of large gauge transformations with non-compact support in gauge theory. Okay. So, I think it's fair to say that although we've made a lot of progress in understanding quantum gravity and the holographic principle in anti-de Sitter space, flat space holography is really still very mysterious. And the reason is just because there are a lot of sort of order one qualitative differences between these two classes of spacetime. So this is sort of a cartoon of asymptotically anti-de Sitter space as opposed to asymptotically flat space. So the first qualitative difference that you can see from these pictures is just that the sort of natural conformal boundary in flat space is null rather than time-like in anti-de Sitter space, and that means there's not really an interesting reflecting boundary condition in flat space like there is in ADS. So flat space really behaves more like an open quantum system rather than a closed quantum system that we are familiar with in anti-de Sitter space. Okay, so one reflection of that fact is that if you look at sort of the natural Hamiltonian functions that you would think generated time evolution along this boundary, they're actually not absolutely conserved, rather they satisfy some balance law. So this quantity is the Bondi mass aspect. It's sort of like the Hamiltonian at null infinity, and rather than being absolutely conserved, it sort of keeps track of the flux of energy momentum through the boundary, because the system behaves more like a null system.
And, you're concentrating on the null boundary, but there is also the space-like boundary and the time-like boundaries.
They're also, you can think of them as sort of corners of these.
Which are corners, but just because the conformal transformation is bad. Right? Yeah. ADM quantities are defined.
There are, absolutely conserved quantities defined on space-like Cauchy slices. The problem with those quantities is that they don't really keep track of the dynamics very well, because as you can see, you can have radiation leaking out, which will be captured by every Cauchy slice, but which sort of isn't captured by these asymptotically null slices. And that's why the Bondi news is sort of
massive particles.
Massive particles, they end up here, but there's a way to keep track of them, sort of by taking a null slice and then capping it off up here with the hyperbola. This sort of known way to blow up spatial infinity in future and past time like infinity using hyperbolas, and the formalism extends pretty naturally for those cases. But massless particles are always easiest, so that's what I focus on. Okay, so the next kind of important qualitative difference is that because this space is non-compact in a very important way, the spectrum is naturally continuous, unlike anti-de Sitter space, which has an effective infrared regulator in a discrete spectrum. And when you don't have a gap in the spectrum, you immediately encounter a range of very subtle, sometimes confusing infrared effects connected to soft particles, infrared divergences, memory effects, and asymptotic symmetries. And these subjects have been studied intensively in the last couple of years. They have very interesting connections between each of the corners of that triangle of ideas. And the reason that so much ink has been spilled on these topics is really because it's the most obvious aspect of quantum gravity in asymptotically flat space that differs significantly from anti-de Sitter space. It really has to be understood precisely to even get started in this subject. Now, probably the most important difference between quantum gravitational effects in anti-de Sitter space and in flat space is the behavior of black holes in these spacetimes. So you might be familiar with the fact that the Schwarzschild black hole in flat space has a super Hagedorn density of states, negative specific heat, and a finite lifetime. So these black holes are really more like long-lived metastable resonances rather than eigenstates. And it's important because in anti-de Sitter space, the black holes, they really give us a window into the universal properties of the generic high-energy state in the quantum mechanics dual to anti-de Sitter space. And really the fact that the entropy of the large ADS black hole scales like that of a non-gravitational conformal field theory is a huge clue to that correspondence. That would really inform your guess if you didn't know anything else about quantum gravity in anti-de Sitter space. So, in flat space, we could have tried to interpret e to the s as the high energy density of states of some putative quantum mechanical dual, but actually the growth is just too fast. As I said, it's super Hagedorn, meaning that it grows faster than energy. And that's just not characteristic of any local quantum mechanics with a sensible UV fixed point. So, that might not be a problem, since really all of these black holes are metastable, but if that's the route that we take, then we lose one of our biggest hints about holography. So, all of those slides are just to say that it's pretty clear that, if there even is a holographic description for the quantum mechanics of gravity in asymptotically flat space, it is going to look significantly different than the quantum mechanics of anti-de Sitter space. And I think it's a fair question to ask whether or not this description should exist at all. But there are a couple of hints which indicate that it should. For instance, for black holes in any space-time, the entropy always still scales like the area rather than the volume. And that was kind of the first coarsest hint about the holographic principle. And there's the fact that the gravitational Hamiltonian is still always a boundary term, even in asymptotically flat space. And we don't expect any precisely defined local observables for quantum gravity in asymptotically flat space. So all of these things, to me, point to the fact that there probably is some form of the holographic principle operating for quantum gravity in asymptotically flat spacetimes. But
the last line of the release statement, I'm supposed to talk about S matrix, right? Doesn't indicate that there should be some kind of theorem in the boundary.
Well, I think it's suggestive, right? I mean, the reason that we say the S matrix should be a well-defined observable in quantum gravity is precisely because it can be defined basically in terms of states just at the boundary, right? And this kind of attack that we're going to take here. Let me say a little bit more about that in a minute. This is not meant to be some proof. It's like why might it be the case that there is some description that doesn't involve local propagation in the bulk of the space-time. But I think, because of all these confusions, we are still very far from any type of precise statement about a correspondence in asymptotically flat space. And I think it's really difficult to know what to expect. And for that reason, most of the work in this subject takes sort of a bottom-up approach, where we take known results about either perturbative gravity or some non-perturbative information regarding black holes, and we kind of try to massage those known quantities into a way that makes them look holographic, and sort of see if we can get any clues about the right formalism or the right frame to be thinking about this problem. Okay. Now, since all of these approaches are bottom-up, they really can't be wrong. Well, that's not the right question. The question is really whether or not they turn out to be interesting or useful for anything. And hopefully by the end of the talk, I'll convince you that there are some very interesting results in this direction that are suggestive of a holographic description, but we still don't have the complete picture for sure. Okay. Any questions? Okay. So, following the analogy with anti-de Sitter space, most attempts at flat space holography try to use null infinity as a holographic plate. So, in anti-de Sitter space, we have a conformal field theory description of the dynamics, which can be thought of as living at the time-like boundary of anti-de Sitter space. The question in flat space is, could we have some intrinsic description of the dynamics in the bulk asymptotically flat spacetime, which doesn't make reference to any propagation in the bulk, which just sort of has an independent definition formulated purely at the conformal boundary at Strat. There are a couple of different approaches with varying levels of success. The one that I'm going to discuss in this talk is usually called celestial conformal field theory. And this formalism is really based on a very simple kinematic observation, which is just that massless particles moving in asymptotically flat space, they come in, they interact, you don't know what happens, they come back out. They pass through stri, the conformal boundary, at isolated points on the celestial sphere. Okay? So it kind of looks like you might be able to formulate this problem in terms of some local operator insertions living at the sphere at infinity. And that's the idea that we're going to investigate. Okay, so just put a couple of equations on that idea. So I'm going to work just in general dimensions, because anything that I say actually works for asymptotically flat spacetimes in any number of dimensions. And we're going to look at massless particle kinematics. So those are just specified by a bunch of points on the forward null cone. And we can pick any parameterization that we'd like for those momenta, but I'm going to pick a particularly suggestive one. So I'll factor out this sort of scale parameter omega, which you can think of as the frequency for these particles. And then I'll choose some flat coordinates on a cut of this cone. So this is p hat. These x's, you just think of them as regular Cartesian coordinates. You can think of them as the sort of the coordinates that you get by choosing sort of this hyperbolic cut of the null cone here, and then inducing the metric on that cut, on the metric on rd plus 1, comma 1. And the metric on that cone, of course, is degenerate. The omega direction is the degenerate direction. That's the null direction going up this way. And then the metric that you get on the cut of the cone is just conformally flat. And the conformal factor is just determined by whatever function of the coordinates that I chose here. So if I chose it to be 1, then it would just be regular flat coordinates. If I chose it to be 2 by 1 plus x squared, then that would be like taking a round cut of the cone. They're related to each other by conformal transformations, so it really doesn't matter what we choose. Okay. So if you choose, for instance, a fixed value of omega, then what you get is just a d-dimensional space-like cut of the future light cone, conformally flat metric. And if we choose this factor to be 1, then the Lorentzian inner product on that cone is just the separation along the space-like cut Okay? So what that means is that the short distance expansion on this space-like cut of the null momentum cone is the same as the collinear expansion for scattering amplitudes. Okay? And scattering amplitudes have a very interesting property that if you take two of the momenta to be very close to collinear, they actually factorize onto the exchange of a bunch of particles into sort of a 3-point amplitude and a reduced amplitude that doesn't know about those two collinear particles. So if you think about what this factorization property looks like on this celestial sphere, it looks like you took two operator insertions on the sphere close to each other and replaced it with a sum over operators at that point. And that looks a lot like the d-dimensional Euclidean operator product expansion.
Does this collinear expansion have finite radius of convergence?
That I'm not positive about. Let me say a little bit more about that later, because you have to be a little bit. Let me discuss the conformal transformation properties of the states first, and then maybe we can discuss that. Okay, but at least at this level about normal statements in the plane wave basis for the scattering amplitudes, it looks basically like an operator product expansion on the celestial sphere.
So, basic question. Suppose you do the opposite. So suppose you assume that this is such an expansion of the conformal theory, because in that case you have much more information.
Yeah.
Does it tell me something about how this collinear limit has to work? So
well,
give me some constraint.
That's what we're basically looking for. So, a lot of the work in this field, because we don't know what the sort of axiomatic definition of this alternate description is supposed to be, sort of takes statements that we know about the perturbative S matrix and translates it. What we want is an independent dynamical way of computing this way, which we then turn into a non-perturbative definition of these amplitudes in quantum gravity. Right? So that's kind of what we have in anti-de Sitter space, where you can calculate boundary correlation functions using the bulk, but really we don't know the non-perturbative definition of quantum gravity in the bulk of ADS, but we do know the non-perturbative definition of Euclidean conformal field theory, which we use to define observables in the bulk. So, at kind of the current status of the field, we're kind of still looking for the axiomatic definition of this description of the theory. And people compute these OPE coefficients using perturbative results, but we really don't have a lot of sort of first principles, non-perturbative things like radius of convergence.
Another question, just to know if I'm understanding. This island that is Euclid island that is inside the I minus there, this would be the snare I plus taking the Mery transforms.
Sorry, I just didn't.
Suppose you this on the celestial sphere you have this island side.
Yeah.
So this is I plus, but strictly speaking is I plus smear after the Mery transforms.
Yeah, that's right. So I haven't discussed the Mellin transform yet, but this is just kind of a cartoon way to remind you that some of these particles are incoming, some of these particles are outgoing, and that is actually an important distinction. There's kind of an extra discrete label coming along with these operators of this Euclidean conformal field theory. Yeah, that's an excellent question.
So when you say collinear limit, both the moments have to be either incoming or outgoing.
Either way. It really is just this one of these. Okay. So, all that's just to say that the S matrix in D+2 dimensions is a quantity with operator insertions on the celestial sphere, but importantly, with an extra label corresponding to energy, which I haven't discussed yet. And you can think of this correspondence sort of either in kinematic space in terms of the null cone, or in position space in terms of the cone that lives at the boundary of spacetime. Okay? And that's really because if you take a quantum field and you push it out near the boundary of the space in the null direction, you'll see, just using basically stationary phase, that the quanta that it's creating all have momenta that are aligned with the direction on the sphere that you're pushing the field out in. So you sort of trade the direction on the null cone for a point on the conformal boundary. So you can think of these x's either as coordinates on cuts of scribe or as coordinates on cuts of the null cone. It's really the same thing. So to sort of simplify the discussion, I'll always just work in momentum space, but keep in mind that this is really the reason why we're thinking of this as a holographic description, is because these space-like cuts are like these space-like cuts of the cut.
It seems one approach to define this non-perturbable would be start from ADS. In principle, one knows how to extract flat space asymmetric by taking flat space.
Well, that's a very dangerous limit. I agree that in perturbation theory, it does seem to make sense and give the right results. But if you want to think about things like black holes, for instance, it's an extremely dangerous limit to take, just because, for instance, the black holes that survive in that limit are the small black holes in anti-de Sitter space, which actually we understand very poorly. Which kind of tells you that non-perturbatively something very tricky actually might be happening in that limit. I think it's actually not that well understood. But there is work basically in reproducing the type of results that I'm going to be describing in terms of limits for anti-de Sitter space correlations.
But do you expect that there should be a non-perturbative limit kind of procedure start?
I'm not sure. I'm a little bit worried that there could actually be a phase transition. I mean, if we actually just think about like a non-abelian gauge theory in anti-de Sitter space, clearly something dangerous can happen when we pull the effective infrared cutoff through the strong coupling scale. Because if it's above the strong coupling scale, the model never becomes strongly coupled. Behavior will be very different if the effective infrared cutoff goes below it, right? And effectively, we'll always be taking the infrared cutoff through that scale when we take this. But that's a non-perturbative thing, which you don't really know, just calculate perturbative Witten diagrams in ADS. So there might very well be an interesting way to take that limit non-perturbatively, but it makes me a little nervous, so I haven't really worked on it. Any other questions? So the sort of last part of this kinematic reformulation is just the observation that in D+2-dimensional asymptotically flat space, the Lorentz group is realized as conformal transformations of the celestial sphere at the bound. Okay, so modulo this question about the Mellin transform that I'll discuss in a moment, we're imagining just rewriting the D+2-dimensional S matrix as a bunch of insertions of local operators on the D-dimensional sphere. And then Lorentz invariance will guarantee that those operators transform like operators in a D-dimensional Euclidean conformal field theory. Okay?
So that locality comes from?
Well, that's why it's in question mark, because we don't really know whether or not these operators have all of the right local properties in a D-dimensional Euclidean conformal field theory.
We even expect them.
I'm not sure that we do. Like I said, I have really no expectations. The first like 4 slides were reasons that I think that flat space quantum gravity is going to be very different from ADS. It could be that we just have a new type of system that we have. We got very lucky in anti-de Sitter space because we, connected a problem that we didn't completely understand to a type of system which has been studied extensively for 50 years. That doesn't have to be the case. Flat space, it might just be a different type.
Then I'm confused because before you were talking about the no P structure.
Yeah.
So you need this operator to be local, right?
No, I mean you can have conformal blocks, right? And where there is no real locality. I mean, conformal block is not local. You can have cuts up the wazoo, and it's only when you combine 2 of them and you sum. Holomorphic and anti-holomorphic blocks, you sum if you are in 2 dimensions.
See, I mean, one definition for locality for Euclidean conformal field theory would just be that you don't have any singularities at non-coincident points on the sphere. If you're working just in the plane wave basis, that actually won't be true because you can have factorization channels where you have a sum of different momenta going on shell that gives you singularity in these things, which doesn't look like it would come from a local operator insertion. But as you mentioned previously, you also need to get the actual right transformation properties to do this Mellin transform, which is like an integral over all energies. And what people don't know yet is whether or not taking that extra change in basis actually does turn these into local correlation functions with all the right singularity structure. I think that's not proven yet.
What about the unitarity of S matrix? Because in this case, kind of there is time on the boundary, so it's clear that bulk unitarity translates into boundary
Yeah.
unitarity. So here time is lost on the boundary.
It's much less clear what that's supposed to mean as a constraint on these correlation functions. In low-dimensional examples, you can say certain things. So I won't discuss it, but for instance, we've done the exact Mellon transform for some two-dimensional integrable models where you can take really every constraint that we know about the S matrix, turn it into a constraint on these correlation functions. You know you're not making any mistakes. There's no room for question marks, but you lose a lot of the structure when you reduce all the way down to 2D.
So it's not clear what unitarity of S matrix translates.
Is there some notion of reflection positivity? So let's just do
Yeah, but it's not clear why it should be related. Because,
Well, you can turn unitarity into statements about growth of S matrix elements and that sort of thing, and those do have reflections in these Mellon transform correlation functions because we're going to take an integral over energies, and then we need to know about the asymptotics of the S matrix in particular kinematic regimes in order to say what we get. But I think there's no sharp, nice statement. Part of that is because we really don't have all of the non-perturbative constraints that the S matrix is supposed to satisfy in asymptotically flat space. There's a lot of things we can derive from perturbation theory, but if I just handed you a class of functions, I don't think anybody knows all of the different things that you need to check in order to actually determine that it's a non-perturbative S matrix. So that makes finding the non-perturbative definition of these quantities even more difficult. All right, so those conformal correlators are going to be model dependent, but some of their general properties will follow from universal statements about the S matrix. So, for instance, all the conformal field theories that we know, they have some small set of universal operators. So, for instance, every local conformal field theory comes with a stress tensor whose job it is to generate conformal transformations on the local operators, and what we'll see is that the existence of that operator in this celestial conformal field theory formalism is guaranteed by a universal statement about the gravitational S matrix in flat space. So I'm going to show you how to explicitly define an operator in celestial conformal field theory that satisfies all the ward identities of a d-dimensional stress tensor. Okay, so that's sort of exactly what happens in ADS. Graviton in the bulk has some universal low energy dynamics, gives you a universal operator in the dual description. Similarly, when a conformal field theory has a global symmetry, local operator spectrum includes a conserved current. And we're going to get those operators explicitly from universal statements about gauge theory amplitudes, in particular soft factorization of gauge theory amplitudes. So that's sort of the spin one universality part of the story. Just as in ADS, if you have a gapless gauge field in the bulk, you get conserved currents in the boundary description. Okay. All right. So now we're just going to do some of those statements, but with formulas. So again, I'm going to just take this parameterization of all the null momenta in the problem. There's some frequency parameter and then d flat coordinates, which parameterize the space-like cut of the cone. And then the Lorentz transformations, they're just realized as conformal transformations on these d-dimensional coordinates. Okay? The important point, which we've mentioned a couple of times, is that, of course, Lorentz transformations also act on this frequency variable, omega. So what that means is that the S matrix elements would transform like d-dimensional correlation functions of conformal primaries, except for these local operators, they don't diagonalize the dilation operator. And that's basically just because, these operators create plane waves, and momentum eigenstates are not boost eigenstates. And if you look what the dilation operator is inside of the Lorentz group, it turns out to be a boost. Okay, so these things will not explicitly diagonalize D. And you can see that if you just write out their transformation properties using the Lorentz transformations, you'll see that where there should be a scaling dimension delta, there's an omega d omega. Okay? Now, for massless particles, you can fix that just by taking a Mellon transform. Okay, so We're basically going to do an integral over frequencies. And you can sort of think of these states as generalized Rindler modes. So normal plane wave states, we diagonalize all of the momentum generators. Here, we're looking at states which diagonalize a particular boost in asymptotically flat space, because we want to diagonalize the dilation operator in conformal field there. Okay, so this is really just, it's kind of like the S matrix, but for a uniformly accelerated observer in flat space. That's another way to think about this if celestial CFT triggers you. Okay, now there are some open questions about the contour that you're supposed to take for this Mellin transform and the admissible values of the scaling dimensions. So when this contour is non-compact, then you have to worry about whether or not there are divergences, and you might have to define things by analytic continuation. There's a certain class of residue operators which you can think of as sort of taking this contour to be compact in the complex frequency plane with an integer scaling dimension. And these operators are sort of intrinsically related to soft scattering states, because what they're doing is isolating particular terms in the Laurent expansion of an S matrix when you expand it in the small frequency limit. Large, small frequency. Okay. So, if there's no questions, I'm going to first discuss boundary currents and how they arise from photons and gluons in the bulk. Then we'll do the boundary stress tensor, and then probably wrap up with the conformal manifold.
Can you remind us why? Can you remind us why the S matrix is the Laurent expansion? That there are no logarithms constants.
There can be logarithms. They usually don't arise at the orders in omega that we're looking at. Yeah, generically there will be logarithms in the S matrix. And you can turn that into actually statements about the analytic structure of the Mellin transformed amplitude. So I think actually Monica has a paper with Nima Handy and some collaborators where they looked at what logarithmic terms do when you take the Mellin transform. It's not going to play a particularly important role here, but it is an important point. Okay, so sort of most universal statement that I know about dynamics of the S matrix with a gapless degree of freedom is soft factorization. So if you have a scattering process that involves a photon, and you take the limit where the photon's wavelength becomes much longer than any other scale in the scattering process, then the S matrix element with that photon factorizes into a reduced amplitude without the photon acted on by a soft operator. Okay? And that's because this long wavelength photon just can't resolve the short distance scattering process. It just sort of couples to the long range conserved quantities of the external hard particles. So the standard statement of the soft photon theorem in abelian gauge theory is just that if I take the omega goes to 0 limit of this amplitude with one photon, it factorizes into this soft Weinberg pole plus order 1 terms, which we don't need to discuss right now, times this reduced amplitude without the photon. And this soft factor is very simple. It's just a combination of kinematic factors weighted by the charges of the external states. Okay. So that's sort of a textbook statement about the S matrix. In the notation that I'm using, this soft photon theorem just says that I insert one of these operators that creates a photon in the celestial sphere, I take its frequency to 0, and I get this kinematic factor times a reduced correlation function. So the name of the game is basically going to be to define an operator in celestial conformal field theory that isolates this Weinberg soft factor. So we can do that either using one of these residue operators that I discussed earlier that picks out the 1 over omega pole. You can equivalently think about it as multiplying by omega, taking the limit omega to 0, or it's actually also been demonstrated that you can do it with a non-compact contour, and you just have to take a particular limit onto delta is equal to 1. No matter which definition that you choose, you get a conformal primary operator with spin 1 and dimension 1, and its matrix elements are controlled completely by the soft photon theorem. Okay? So if you just plug in my parameterization for p and epsilon, you'll find that insertions of this soft photon operator is basically just a derivative of the logarithm with an argument, just the separation on the celestial sphere. Okay? So this statement is just completely equivalent to Weinberg's soft photon theorem. Now, what we're interested in is a conserved current in a d-dimensional Euclidean conformal field theory. And that's a conformal primary operator with dimension d minus 1, spin 1. And its sort of defining property is that it satisfies a shortening condition. So if you take its divergence, particular descendant inside of a correlation function, then it'll only have contact term support, where you have other operators which are charged inserted at those points. And the coefficients of those contact terms are just the charges for those local operators. Now, this isn't quite the soft photon theorem, but it does seem to be related, right? Up here we have sort of on the left-hand side, correlation function with an extra operator. On the right-hand side, correlation function without that operator, but with the sum of charges and kinematic factors. Okay? So, the kind of trick to understand the relationship between those two is just to multiply both sides of the word identity for the conserved current by the derivative of a logarithm, and then integrate with respect to the argument of the logarithm. So if I do that, and I use the fact that this is just a delta function, then that'll turn the first line just into a derivative of a logarithm. This argument is just the separation on the celestial sphere, but that was just the matrix element for the soft photon that we already knew about. So if I just integrate by parts in this formula and move the derivative off from j onto the log, then I'll get some funny integral transform of the conserved current being equal to the soft photon operator. Okay? And it turns out that two derivatives on the logarithm is actually the conformally covariant tensor. It's a very natural quantity in d-dimensional Euclidean conformal field theory. And actually, this integral transform is actually known in the conformal field theory literature. It's called the shadow transform. So this is an operation which, if I give you a conformal primary with dimension delta and spin s, you do this integral transform, you get back something which transforms like a conformal primary with spin s dimension d minus delta. You remember the soft photon operator had dimension 1, the conserved current had dimension d minus 1, so that's kind of the natural relationship that you'd be looking for. Okay? Now, an important property of the shadow transform is that if you do it twice, you get back the original operator that you started with up to some normalization factor. So if I knew that the soft photon operator was the shadow transform of the conserved current, I can equivalently just write the conserved current as a shadow transform of the soft photon operator. And once you arrive at this formula, then you can forget about all of the integration by parts tricks that I was doing earlier and just check that the operator defined this way satisfies all the word identities of a conserved current in Euclidean conformal field theory. So this is an explicit definition for a conserved current within celestial conformal field theory, and its existence is guaranteed by the universal properties of gauge theory scattering conditions. Okay? So just like in ADS, when you have a photon or a gluon, the same basic manipulations work for non-abelian gauge theory. When you have a gapless gauge field in the bulk, you get a conserved current in this boundary description. Okay? So what about the stress tensor? Does it work similarly? Well, in quantum field theory, the job of the stress tensor is to generate space-time isometries or conformal isometries on the operators in the system. And in our construction, the Lorentz group generators are the things which generate conformal transformations on these operators, right? And it turns out that the Lorentz group generators show up in a universal statement about graviton scattering amplitudes in asymptotically flat space. Okay. So soft graviton theorem actually has two universal terms. One, the normal Weinberg pole, which I'm not going to discuss for the moment, and a subleading order 1 piece, which involves the angular momentum operator acting on all of the different external states in the scattering process. So this is a little bit of a messy formula. Epsilon is just the polarization tensor, and this guy is just the angular momentum operator acting in whatever spin representation the particles transform in. Both of these are totally universal and model independent. They depend only on the conserved quantum numbers of the external states. Precisely because this fact that the graviton's wavelength is just so big, it can't resolve anything else about the quantum state. Sure. So, based on what I showed you about the conserved currents, it seems natural that this sort of subleading soft graviton operator that isolates the order 1 piece in the soft graviton expansion should be related somehow to the stress tensor. Now, the matrix elements of this subleading soft graviton operator are much more complicated than the soft photon operator. You don't need to look at the details of this formula, just know that it's significantly more complicated and more tedious calculation, but at the end of the day, what you can show is that this soft graviton operator is precisely the shadow transform of an operator that satisfies all of the word identities of a stress tensor in the d-dimensional Euclidean conformal field theory. So another way to say it would be, if I take the matrix elements of the subleading soft graviton operator, and I take the shadow transform to compute the correlation functions of this operator, which I'm calling T, you'll be able to show that it satisfies all the word identities for a stress tensor. Okay? So it is a stress tensor.
So how do you check this in practice?
The way you check this in practice is you take, so we're going to take this definition, we go here, we use this matrix element for B, we do this non-local integral transform on all of these things. That gives us an expression for the correlation function involving T, and then we take divergences or traces, whatever, and you get exactly contact term support with the right coefficients.
What happens? Let's say it's an abelian theory which confines the delta.
I will discuss that. Well, there's a way of thinking about, and I don't know if I'll have time for this, but there's a way of thinking about soft limits in gauge theory and gravity, sort of as taking a derivative with respect to a space of vacua. It'll be more clear once I discuss the nonlinear sigma model. And the statement in a gauge theory which confines would just be that that space of vacua disappears non-perturbatively. So it sort of looks like it's there in perturbation theory, because when you're doing perturbation theory, you're always implicitly in the Coulomb phase with long-range gauge fields, and it looks like there's this vacuum degree of freedom corresponding to long-range gauge transformations. But if the theory develops a gap, then that space of vacua is just, you can only have one point. Let me do the nonlinear sigma model, and then it'll be able to make that a little bit more precise. Are there any other questions?
Can people consider like multiple soft particles?
Yeah, so that's exactly what I want to discuss next. Yeah. So that is the most clear in the nonlinear sigma model.
So people know how to compare it to the conformal correlator or the stress tensor and current themselves.
Yeah,
and
so
see
the
how they rise from the multiple soft.
a thing that confused people for a long time was that in abelian gauge theory and in gravity, if you take multiple soft limits, they don't depend on the order in which you take the limit. Which sounds good, because then these currents and these currents which I described sound like they have unambiguous correlation functions. But in non-abelian gauge theory, if you take two gluons to be soft, it does depend on the order. So there's an antisymmetric double soft limit, which is universal, but it confused people because people thought, well, that sounds like the non-abelian currents are going to have ambiguous correlation functions. But there's a geometric way of thinking about the antisymmetric double soft theorem, which is basically computing the curvature in a particular geometric space. And in non-abelian gauge theory, the statement that those limits don't commute is just the statement that the space of vacua in that model is curved. So it's actually very natural, and it kind of, let me discuss that a little bit later. It is, I think, understood now. Okay, so we discussed spin 1 and spin 2 universality in this formula. In this formalism, what would the sort of spin 0 universal operators be in celestial conformal field theory? Well, spin 0 operator is really an operator that you can use to deform the model. And in the context of celestial conformal field theory, global conformal group is just the Lorentz group, which can't be violated. So really the only interesting deformations in this formula are the ones that preserve conformal invariance. Those are known as exactly marginal deformations, and the space of all conformal field theories related by exactly marginal deformations is the conformal manifold. And so what we're going to see is that the universal statements about the S matrix when there's a gapless spin 0 particle translated into the celestial conformal field theory language just tells you about the conformal manifold. Celestial conformal field theory. So it produces for you the exactly marginal deformations. Okay. And again, that's a statement which is exactly the same in anti-de Sitter space. So if you have a continuous space of vacua in the bulk gravitational theory in ADS, that gets mapped onto the conformal manifold of the dual quantum mechanics. Just think about n equals 4 and the gauge couple.
Okay. But if these massless scalars, if they're goldstones, like times or something.
They're not. Goldstones are very different from a generic space of vacua. So goldstones usually come with a locally symmetric metric, and they have an Adler 0. That's a special case in terms of a generic vacuum manifold, actually. So you don't have an Adler 0 for all nonlinear signal models. You have it for a particular class of metrics on the target space. And that corresponds to a particular fact about the holonomy and the conformal manifold in this.
So what happens for those? Because there is no different CFTs, right? Because
well,
all vacua equivalent.
It's kind of trivial, yeah. Nothing changes when you move around because they're just related by asymmetric transformation. But in quantum gravity, we actually really don't expect global symmetries, so it's not clear that that example for a vacuum manifold is the most interesting.
What it will correspond to an isometry in the logical metric or something like that?
Yeah, so you have G mod H, but you had a bi-invariant metric on G, so there's still another action of G on that space. So you can, if you're at one point, then you can move around to all the other points using an isometry. But that's not generically the case for any vacuum manifold that has entirely flat space. It's something that you get by putting particular requirements on the metric. All right. So just to say very briefly where we're starting, in asymptotically flat space, the vacuum is determined basically by boundary conditions, or equivalently vacuum expectation values at spatial infinity. And the long wavelength fluctuations about those boundary conditions are described by a sigma model whose target space is just the vacuum manifold. Yeah, so this is just the geometric nonlinear sigma model. G is the metric on the space of vacua, and so M comes with an intrinsic geometry, which is just the curvature of this metric. It's going to turn out that that will be precisely the geometry of the space of celestial conformal field theories. Okay. So when you actually try to do perturbative calculations in this model, you expand all the fields about their BEVs, and then you integrate over the normalizable fluctuations. When you do that, you can express the action in terms of all of the curvature invariance of the model. Now, infinitesimal variations along the bulk moduli space, they're really just captured by long wavelength scalars, because if I do this expansion and then I take the wavelength of this mode to be very long, that's equivalently just like shifting this VEV, which I fixed at the boundary. So the zero mode of the normalizable fluctuation is really just like infinitesimally shifting the boundary condition, right? Which means that if you want to move around in the bulk moduli space of vacua, you just excite soft scalar degrees of freedom. Okay, so that's the right-hand side of this picture. You want to move around in the space. insert a soft particle. Now, those soft particle S matrix elements are actually going to be totally controlled by the moduli space geometry. That's a known fact about the nonlinear sigma model. And that's going to allow us, just like in gauge theory and gravity, to define some universal distinguished operators in celestial conformal field theory, whose role is just to generate marginal deformations around the conformal manifold of celestial conformal field theory. This is kind of the cartoon for what we're going to do with formula 2. Okay? So there's another universal statement about the S matrix when you have a gapless scalar particle. What it says is that when you take the frequency of one of these moduli scalars to 0, it comes out of the correlation function and is replaced with a covariant derivative of the S matrix with respect to the vacuum parameters. Okay? So when you have a moduli space of vacua, the S matrix comes with an extra label, which just tells you which boundary conditions do I use when I compute this S matrix element. And this derivative operator is just acting on the S matrix element as a function of these boundary conditions. Okay? So the soft theorem says you take the infinite wavelength limit of a soft moduli scalar, that just gives you a derivative of the reduced S matrix element. Okay? And the physical interpretation of that statement is simple. The zero mode of the moduli scalar is just the vev. So if you excite the zero mode, you just shift the vev a little bit. That moves you around in the space of vacuum. Okay? So now I'm going to play the same game that I did in gauge theory and gravity and define some soft moduli operator in celestial conformal field theory that isolates this universal statement about the S matrix. And you can see that it will have dimension 0, which means that its shadow transform will be a spin 0 dimension D operator. That's also known as a marginal operator. So we can really think about this soft moduli scalar as being a D-dimensional integral of a marginal operator. That's exactly the type of thing that you add to the action in conformal perturbation theory to move around in the space of conformal field theories. And the correlation functions of the soft operator, they're just covariant derivatives on the reduced image. All right. So in this language, turning on a coherent state of soft radiation just amounts to actually parallel transporting around in the space of bulk vacua. If you're just doing it in a particular direction or just working infinitesimally, then you just exponentiate that soft operator. That turns on some coherent state of soft radiation, and that moves you a little bit around in the space of vacua. But if the vacuum manifold is curved, then actually there's path dependence in these deformations. Okay? In other words, there can be holonomy when you go around in a little loop in the conformal manifold. And the way to compute that just using the S matrix is exactly with this antisymmetric double soft limit. So this is just a formula which you can prove in the nonlinear sigma model. And what it means is I take this amplitude with two moduli scalars. I first take the soft limit in the I direction, and then in the J direction, and then I anti-symmetrize, do it in the opposite direction. And what that's doing in terms of the vacuum geometry is just parallel transporting around in a little parallelogram in the space of bulk vacua. And the small parallelogram limit is just the curvature evaluated at that point. Okay? So antisymmetric double soft in the nonlinear sigma model just computes the curvature of the vacuum manifold at that point. Okay? And that's going to be a very important geometric way about thinking about antisymmetric double soft in gauge theory. It's kind of a way to understand that there really is this moduli space of vacua in gauge theory, which is a little bit confusing to think about, but you know it's there just because this thing computes its curvature. Okay, is that, okay, yeah, one more slide. So this formula here probably looks very familiar to you in terms of conformal perturbation theory, right? Because if I expand that exponential out, then it's just, n powers of the interaction. And that's basically the definition of correlation functions in conformal perturbation theory. So if you have a model and you have an exactly marginal deformation, you can add it to the action, and then the Euclidean correlation functions infinitesimally displaced from the point that you started are just defined by inserting e to the minus s in the correlation functions in the original model. And then you can expand that exponential out, do perturbation theory in the conformal field theory, and that allows you to move around in the conformal manifold. Okay, but these formulas are exactly the same as we have in the nonlinear sigma model, sort of reduced by 2 dimensions. Okay. And in particular, if you just take conformal perturbation theory, do it to first order, that tells you about the derivative of the correlation functions, which was exactly the solved theorem in the nonlinear sigma model. And of course, so we had non-trivial holonomy if the vacuum manifold was curved. If we have a conformal manifold, there can be basically barrier curvature where we sort of do a closed loop in the conformal manifold. That also computes the curvature and is equivalent to the antisymmetric double solve. So this is the last piece. I've only got about 5 minutes, so I'll be kind of brief, but this is kind of the answer to Yifan's question. So I want to basically use this geometric perspective that we had from the nonlinear sigma model and its finite dimensional space of vacua to understand some older statements about the relationship between the BMS group and infinite dimensional spaces of vacua and soft graviton limits. So, there is this claim in certain corners of the literature that gauge theories in the Coulomb phase and gravitational models in asymptotically flat space have infinite dimensional spaces of vacua precisely related to gauge transformations with non-compact support, or in the case of gravity, the BMS group, which is basically a set of diffeomorphisms with non-compact support. Now, because they're diffeomorphisms, you know that they basically have to be related to the zero energy sector of the theory, because all it really knows about is the boundary. Locally, everything is indistinguishable. And the idea will be to reinterpret all the soft photon, gluon, and graviton limits as functional derivatives of the S matrix elements with respect to this infinite dimensional space of vacuum. Okay? That idea is kind of already implicit in the statement that the soft graviton theorem was the ward identity for the BMS group. But it's not really been phrased in this language, and because it wasn't phrased in this language, the non-abelian gauge theory case confused people for a long time, but I think now it's clear what's going on. Because in non-abelian gauge theory, the multi-soft limits do not commute, just like in the generic nonlinear sigma model case. And in this language, what that means is just that the space of vacua in non-abelian gauge theory in the Coulomb phase is curved. The antisymmetric double soft gluon theorem can just be thought of as computing that curvature. It's just two anti-symmetrized infinitesimal deformations in the space of these vacua. And so in other words, the Feynman diagram calculations, they not only know about this space of vacua, which some people are skeptical about, but you can actually use them to compute this curvature. Okay. So here's the idea in a little bit more detail. So the Yang-Mills S matrix in the Coulomb phase, where we actually have long-range gauge fields, you can compute it in perturbation theory, and it's totally unambiguous for all finite non-zero momentum. But as I mentioned, the multi-soft limits depend on the order of limits, and so in principle they're ambiguous. You don't know how to sort of extend the definition of the Yang-Mills S matrix onto its boundary in the sort of zero frequency limit. Now, that ambiguity is also universal, and it's basically completely captured by the antisymmetric double soft theorem. So when the gauge group is non-abelian, the right-hand side doesn't vanish, but there's a formula for it in terms of the generators of the gauge group G. And for a while, at least within the celestial conformal field theory literature, but I think also really more generally just in terms of the definition of the Yang-Mills S matrix, this caused a little bit of confusion. And so it's basically a question of what is the right or most natural extension of the S matrix to the boundary of its domain of definition. Is there some good definition for that? And the idea is that no, there's just no canonical extension. basically for the same reason that there's no universal way of relating 2 points on a curved space. So the idea is that all the amplitudes in Yang-Mills theory, when you actually have gapless degrees of freedom, they're tensors on some bundle over an infinite dimensional space of vacua, which, as I'll describe in a moment, is basically labeled by flat G connections on the celestial sphere. So that's a statement which has more or less been understood, at least classically, for a couple of years. So, what I want to say is that inserting a soft gluon in the S matrix is basically just parallel transporting the S matrix about this infinite dimensional space of vacua. And the antisymmetric double soft limit is just computing the holonomy around an infinitesimal closed curve in this huge infinite dimensional space. So you take antisymmetric double soft, that's like taking these covariant functional derivatives with respect to these vacuum parameters of the amplitude. So in this formula, these flat connections are just local coordinates on the vacuum moduli space. And the fact that the right-hand side doesn't vanish just means that the vacuum manifold is curved in Yang-Mills theory. Okay? So in other words, there is no right definition for multi-soft limits in non-abelian gauge theory, just like there's no right definition for parallel transport in a curved space. The answer depends on the path that you take, and the antisymmetric double soft limit just quantifies that discrepancy. Okay? And in that language, the vanishing of the antisymmetric double soft theorem in abelian gauge theory and gravity is really just a statement about the flatness of the space of supertranslation vacua, and the vacua in abelian gauge theory are related to large U1 gauge transformations. Okay. So let me just do this. All right, so let me just describe very quickly the abelian case and then tell you the analogous statement in non-abelian gauge theory. So the subtlety in abelian gauge theory in a non-compact space is basically that there's a tiny piece of the phase space that people usually ignore. So if you look at how the field should behave near infinity, there's always going to be a radiation piece, which comes at some power of 1 over r. But there can be a leading piece which enters before the radiation piece in this large R expansion. And if you want finite energy configurations, then it turns out that this piece can't actually depend on time. It's kind of a non-dynamical degree of freedom or a non-normalizable mode, so it's a boundary condition. And normally what is done when we quantize gauge theory is we just set this degree of freedom to 0. And that's fine, that's a consistent boundary condition, and you can calculate with it. But the fact that you can set it to 0 tells you basically that we're also allowed to vary the S matrix along this flat direction in field space. And what's going to happen is that the soft photon theorem is basically going to be a covariant derivative with respect to this non-dynamical degree of freedom that labels S matrices. Okay? So this boundary condition for generic flat connection on the celestial sphere is invariant under the global gauge transformations, but it spontaneously breaks all the other ones with non-compact support. So in this case, the vacuum geometry is just the space of flat connections on the d-dimensional sphere, which is basically the space of large gauge transformations mod U1. Okay? So the S matrix elements in abelian gauge theory, really they come with this extra label. It's implicitly always 0, but we're allowed to consider infinitesimal variations off of 0. And when we do, we expect that the soft photon insertion should basically be taking a functional derivative with respect to that boundary condition. Okay? And it turns out in abelian gauge theory, because the infrared is exactly solvable, you can work out explicitly how the S matrix elements depend on this boundary condition. Because it's effectively non-dynamical, it has a very weak effect on the S matrix. You can calculate exactly how the S matrix depends on it and just show explicitly that the soft photon insertion takes a functional derivative with respect to the flat connection at the boundary. An equivalent way of saying it would be that this boundary condition, this non-normalizable mode for the gauge field, acts as a background gauge field for the U1 current in the model. That's a familiar statement in anti-de Sitter space as well. When you have a field with a normalizable mode and a non-normalizable mode, the non-normalizable mode, if you turn it on, acts as a source for the normalizable mode in the dual conformal field here.
Do you always just take the connected component of this vacuum manifold that includes the trivial C? Because for T equals 3, for example, non-Euclidean case, there could be different sectors. They go by the winding numbers.
That's a good question. I haven't really thought about that. These are all done, yeah, all the calculations that are
Because
done in
you
the
want to set
literature
C to
are
0.
sort of deformations around this origin point and the kind of connected piece. Yeah, I haven't thought about the disconnected. That's a good question. Okay. Yeah, so the formula for shifting the boundary condition in the S matrix is basically you just turn on a bunch of soft photons with this source. The only difference with the nonlinear signal model case is now the source has position dependence. So we can think about this sum as sort of an infinite dimensional sum rather than the finite dimensional sum that you had in the nonlinear signal model. The integral over the position is just like this extra sum over this infinite dimensional space. Again, antisymmetric double soft vanishes, so the space is flat. All right, so let me just jump to non-abelian gauge theory. So there's a similar sort of non-dynamical degree of freedom or boundary condition in non-abelian gauge theory. It's basically labeled by flat G connections on the celestial sphere. And because it leaves the global part of the gauge group unbroken, the moduli space is map SD into G mod G. So it's some huge infinite dimensional quotient. And the S matrix elements, they implicitly all have this extra label. They are always computed with C is equal to 0. So that's sort of the normal statement of the soft gluon theorem at that particular point in the moduli space. And so the interpretation of the non-commuting antisymmetric double soft gluon theorem is just that it's really computing curvature in this infinite dimensional space of flat G connections. It has a simple formula, and it has, of course, sort of the characteristic features of infinite dimensional curvature. And so the new point, since I'm over time, is just that we'd like to interpret this formula as the curvature of this big infinite dimensional space at the point.
So this I is the one that is related to the shadow transform of the tensor.
This
Tensor.
Yeah, so this is the conformally covariant tensor. Yeah, it's two derivatives of the logarithm. Yeah. Okay, so that's kind of the thing that we gain from this geometric perspective from the nonlinear signal model is that we also have now a geometric perspective for antisymmetric double soft in non-abelian gauge theory. So to end, I just want to say quantum gravity in asymptotically flat space seems to have a lot of very tight structural similarities with quantum gravity in anti-de Sitter space. Gluons give you currents, gravitons give you stress tensors. Symmetry structure in flat space is a little bit more intricate, which is why we have these interesting infinite dimensional spaces of vacua, but all of the statements still fit into that geometric framework, and now we have kind of a nice geometric perspective for antisymmetric double soft in Yang-Mills. It's just an infinite dimensional curvature calculation. So I'll end there.
Questions?
I have a very general one. According to the last advances, what do we know with CFTs? Do we know like about very basic single unitarity, whether it is or not logarithm unique, it is not unitary?
So there is a statement which is that there is a complete set of wave functions, which are these conformal primary wave functions with scaling dimensions on the principal series, so d over 2 plus is. We know that you can decompose any field that has a complete basis, so we know that we can compute the S matrix for those values of delta. It's a little bit confusing because then we have a conformal field theory with a continuous spectrum, which is something which we don't encounter very often in garden variety Euclidean field theory. There are examples like Louisville, but they're much more difficult to understand in models with discrete spectra. It's also a little bit confusing because all of the interesting operators that I've described here do not lie on the principal series, right? They're integer dimensions rather than complex scaling dimensions. And I think it's still not really understood what should be the complete set of operators in this celestial formal field theory. There have been a couple of papers lately trying to argue that sort of just integer scaling dimension operators are enough, but I haven't studied those papers carefully enough to know whether or not it's
Just because I have a very basic sorry, because it's a very basic question, but since we started trying to find some analogies in radius CFT, this case wouldn't be some analog to a large n limit, like 1 over c or something like that, right?
yeah.
Clear what it would be.
I mean, that's another place where it's a little bit confusing, the analogy with ADS CFT, because in pure gravity in flat space, we don't have a dimensionless number like c, right? Because all we have is Newton's constant. We don't have an ADS radius to get something without dimensions. So it's not really clear what the analog of 1 over n is supposed to be. And it's not also really clear whether or not we're supposed to expect some sort of strong coupling in this Euclidean conformal field theory. If the spectrum really does just include all integer dimensions, then there's no real.
The argument of not having another scale is more important for the top coupling, right? Not for the large, because L over G in that case would be related to the K, to the level of
Well, I just mean that
not like
G over L is like the central charge in ADS3, and we don't have something like that in flat space. So it's not clear what like the analog of large anomalous dimensions is supposed to be in this story. It could just be that you just have operators all on the principal series. You have to use them all, and there's some other manifestation of having approximately Einstein gravity in the bulk, which gets cooked in a different way. People haven't really made much progress on that.
You mentioned low dimensional case. What happens in 3D? Because asymptotically flat gravity in 3D is very confusing, right? It's not clear there is a symmetric there because of this conical singularity, like it's not asymptotically even flat. And it's really weird, right? So
yeah, 3D, I haven't thought specifically about.
Yeah, because you don't also have the stress tensor.
Yeah, you're going to have it's like a CFT1, which is not really, well, it's going to be as confusing as ADS2 CFT1. That's kind of the same reasons. I can tell you something interesting about the two-dimensional case, which actually is related to your work. So we took some integrable 2D S matrices, and then 2 dimensions, this Mellin transform is actually just a Fourier transform in the rapidity variables. So you can just explicitly do a bunch of Fourier transforms. You get these Rindler S matrices in 2 dimensions. And they have some properties which are nice, but they also kind of distributional in some cases because you don't have particle productions, you have bad behavior at large rapidities. But if you couple them to JT gravity so that you get this rapidly varying phase, that actually smooths out a lot of the singularities in these correlation functions. So it's sort of coupling to the simplest version of gravity, which induces these rapidly varying phases, which we also think will happen in higher dimensions, makes the correlation functions better behaved. So it might also be true in higher dimensions that when you have black hole production, so you have exponential suppression of 2-to-2 scattering and also rapidly varying phases, that actually coupling to gravity makes this a better defined problem than just a pure quantum field theory calculation, and that's kind of what we would hope. It's sort of the same story in anti-dissolutions. I think there are some people who have thought about the 3-dimensional case, but I just haven't really
Is your understanding of like universal properties like conformal anomalies associated with correlation function with stress tensor from the ball? Remember, there's like even in the 4D 2D case, the center charge in the celestial CFT, there was some kind of debate on what that value is.
Well, you see, yeah, it's a little bit tricky. It was confusing precisely because, so, you know, soft limits for the stress tensor, so the stress tensor is related to the subleading soft graviton theorem. Because that's related to a non-abelian group, they also won't commute, so it's very delicate to understand the TT-OPE.
So is there an extension of what you talked about in last?
Well, I think what should happen, you see, my hope, and this hasn't been explicitly checked yet, but my hope is that although the antisymmetric double soft limit doesn't vanish, you know, the soft operator is not really the good operator in celestial CFT. It's the shadow transform of the soft operator. That's like the nice local Euclidean current. And what I hope is basically that this thing is in the kernel of the shadow transform for the spin one operators, so that actually the correlation functions of the non-abelian currents are completely unambiguously defined. You can talk about their OPE. And I think a similar statement should be true for gravity as well. But the problem is that you need to take this very complicated integral transform twice at this subleading order, and I think it just hasn't been done cleanly. But in principle, that's how you should do it. I think the thing to do is not to try to extract it just from the double subleading soft graviton theorem. You really need to look at the right operator and take its OPE in the shadow transform basis, and hopefully that gives you an ambiguous computation for the TT. But yeah, so that's something which needs to be done. I think it will be done.
More questions? So let's end the game.